Okay, so hi everyone, welcome back. Um, so just a couple announcements before we get started. So the first is that the TA has put together some solutions for homework 1. I haven't had a chance to post them yet, but I will post them this afternoon, and then you can take a look. He's also going to try to get the grading done as quickly as he can so that you can see basically what we expect from you solution-wise before the next homework is due. So please take a look at the solutions. Some suggestions too for some format. So if you read through the solutions, you can see what he has in mind. Also, so just a reminder that we will also have a midterm in this class. So it'll basically take place right after the next homework is due. It'll be a short take-home exam where you just have sort of a compressed timeline to do the exam. Probably a few days. I don't know. I'll send out more details as we get a little bit closer to the date. There's nothing really to stress about it. You know, if you've been kind of following along so far and you've done homework 1 and 2, you should be okay. It'll be very similar in difficulty to the homeworks, just sort of a more compressed timeline. Okay, so today we're going to wrap up just some final thoughts about duality and then start the next topic. So if you remember where we were last time, we were talking about solving, algorithmically, optimizing using the dual formulation. So we spent basically the last, 2 weeks, right, talking about duality, and we were just I was just putting together some closing thoughts about how the dual is used algorithmically in practice. We saw one approach last time. So because the dual is defined as the infimum over a set of functions that are linear in the dual variables. So here the Lagrange multipliers, this piece right here is linear in lambda and nu. And because you have the infimum over a collection of linear functions, that's concave, right? It's sort of the opposite of the result that the maximum of a set of convex functions is convex, the minimum or infimum of convex functions is concave. So we can this is a concave function. It's obtained by computing the infimum, and we can just apply projected subgradient ascent basically to maximize this. So this is what we saw last time, right? To do this, right, we have to compute the subgradient, which requires us to find the infimum, which means that as a result, we can really only apply this particular strategy if the infimum exists, right? So if you can solve this optimization problem and it makes sense. Right, we saw some examples of this last time where for certain values of lambda and nu, right, the solution was equal to negative infinity. If that's the case, right, then you can't solve this problem, right? If you would get back negative infinity as a solution, you can't really step effectively in that direction. So in other words, you basically can only really apply this to situations where the Lagrangian is bounded for all possible inputs of the Lagrange multipliers. And then after that, it's just the standard projected subgradient approach, right? The lambdas have to be greater than or equal to 0. So you compute the gradient of the Lagrangian with respect to lambdas, and you take some small step in the direction of the gradient, right? This is gradient ascent, so there's no minus sign here. We're taking a step in the direction of the gradient, so this is the direction of steepest descent. And then we do the same thing for the nus, but they're unconstrained, so it doesn't require a projection. So the example that we saw last time was the one from class, where we just applied this to see what the sequence of iterations would look like if we applied the dual subgradient method to this simple problem of computing the projection of a point onto a collection of box constraints. So it's pretty straightforward. We just compute actual updates. I wrote them down here, what they actually are. and then just the first few iterations. You can see with this that we already know what the answer is. We in fact solved this optimization problem and saw that it has a closed form solution, right? Where if you have a value of the vector x that's larger than the upper bound, you just set it to the upper bound. If you have a value of any value in the vector x that's smaller than the lower bound, you set it to the lower bound. And that's indeed what's happening here. So in this example, the upper bound was 1 and the lower bound was 0. It was a two-dimensional vector. We hit the point 2 minus 1. And we can see that as the iterations proceed, right, we're getting closer and closer to basically the projection. One thing that I don't think I had time to point out last time, because we kind of rushed a bit through this example right at the end, is that unlike the other methods we saw, like the projected gradient method and the Frank-Wolf algorithm, right? So those algorithms for solving the primal problem, you'll note that the constraints, right, of the primal problem are not satisfied here, and they won't be satisfied until we get arbitrarily close to convergence. Right? So what do I mean by that, right? So that you see the sequence of iterations we've produced, right? None of the components of this sequence actually respect the constraint that the vector x is less than or equal to 1 and greater than or equal to 0, right? You can see that we're making progress every time, but the constraint isn't satisfied. This is, I guess, a bug or a feature of this method, if you want. So oftentimes in practice, when these kinds of dual subgradient methods are being applied, there will also be some kind of convergence criteria that assesses how well or how tightly the constraints are satisfied at optimum. So there's some error threshold saying that you can't violate any of the constraints by more than epsilon as one of your stopping criteria. An alternative to this dual subgradient method, which is actually much more popular in practice, basically because the dual subgradient method has these somewhat unfortunate behaviors, and you have to solve the optimization problem, right? You actually have to minimize the Lagrangian over the primal variables for fixed dual variables. An alternative approach is based on something called the augmented Lagrangian. So the idea is like this. Recall if we had a constrained optimization problem of the form minimize some objective function f naught of x subject to the constraint that ax equals b, right? We would formulate this with the Lagrangian, right, where we add one Lagrange multiplier for every one of the equality constraints, right? The augmented Lagrangian approach is basically to take the objective function and add to it a penalty that looks like rho times the norm of ax minus b squared. The rho here is a tunable parameter, and for our purposes, it just has to be chosen so that it's greater than or equal to 0. You'll note that the addition of this term to the objective function actually doesn't change the problem, right? At any feasible point, it must be that ax is equal to b. So for any feasible point, it must be that the norm of ax minus b squared is actually equal to 0. So we've effectively just added 0 to the objective function, right? And we haven't changed anything else. However, after we do this, we get a new term in the Lagrangian, right, that corresponds to the norm of ax minus b squared. And the method proceeds by basically performing gradient ascent and descent on this Lagrangian sort of simultaneously. So what does that mean? Well, we compute the gradient with respect to x, and we perform gradient descent on the primal variables x. And for the dual variables, we perform gradient ascent, right? So we compute the derivative of the gradient of the Lagrangian. Oops, that should be a new. With respect to the Lagrange multipliers, and take perform a gradient descent basically on the dual problem. The nice thing about this approach of adding this norm squared term is that it doesn't require us to solve that minimization problem. So we don't actually end up with a subgradient method here, right? If f is a twice continuously differentiable function, so it's nice and smooth, or even singly differentiable, right? Then we can apply standard gradient ascent here, and we don't have to worry about doing the subgradient thing. So again, the reason to prefer something like this is that the subgradient methods, although they have sort of the same kinds of guarantees as the regular gradient method, right, and that they all result in convergence with an appropriately chosen step size. In practice, the gradient methods often have a higher rate of convergence, so they converge more quickly to the target. Okay, so that's really all I wanted to say about optimization with dual problems. Are there any questions about this augmented Lagrangian approach or the dual subgradient method? So these two approaches and lots of variants of them can be found in many different places. A lot of different optimization packages will use something like these kinds of approaches when they solve sort of generic constrained convex optimization problems. You'll note that this formulation as well doesn't enforce the constraint, right, and accepts at convergence again, right, because the sequence of the x's is produced by simply performing gradient descent on the Lagrangian, right, which doesn't enforce the constraints except at convergence. This particular approach with the augmented Lagrangian turns out to have much better stability properties in practice, which is why which is really the benefit of adding that ax minus b norm squared term to the objective, even though it doesn't change the problem. Just sort of makes it more smooth by adding a really nice convex function, right, to whatever our original convex function was. Questions? So I know we've been spending a lot of time on duality, but today for the rest of today, we're really going to spend our time on a new topic, which is slightly easier and has a lot more pictures and a little less formulas for a while, just to give us a little bit of a break from doing too much math. Before we jump to that, though, I just want to make sure there's no final questions about these dual optimization problems or anything about duality. Okay, I will take your silence to mean that there are no questions. Okay, so today we're going to start talking about what are called second order methods. So far in this class, our primary tool for solving optimization problems has been the gradient descent method or one of its variants, right? So either projected gradient descent or the Frank-Wolf algorithm or some variant thereof, right? We just saw two methods, right, which were just gradient or subgradient methods, right, applied to a different problem formulation. We call methods like gradient descent, and basically anything that is based on simply computing the gradient in order to determine appropriate descent directions, we call those first order methods. The reason we call them first order methods is essentially, right, when we were doing gradient descent, right, the argument for this was that we would take our function, we'd approximate it locally with its first order Taylor expansion. That gives us basically a supporting hyperplane or a tangent line. That tangent line basically gives us information about, right, how quickly the function is changing locally and which directions it is increasing or decreasing in. And then we just took a small step in a direction that the local information tells us that the function is decreasing in. So one thing this doesn't tell us is it doesn't tell us anything. It doesn't use any information essentially about how quickly the gradient is changing, right? So basically what we would call the curvature of the function is in a particular region. So why does that matter? Well, we saw some illustrations of gradient descent for a variety of different problems, and one of the real issues of the method is that the step size that you take, right, can really drastically depend on how quickly the function is changing locally. So here's an example, right? If you have a function that looks sort of like this, right, then if you're at this point, it makes sense to sort of take small or relatively large step sizes, right? Because the function is kind of bowl-shaped, and locally the derivative is quite low, and in the more global sense, right, the function really is it's not like sort of increasing dramatically. Compare that with a function that maybe looks like this, right, where here, if we take too large of a step size, for example, right, the derivative is much larger. We take even a small step size, right, might move us very far away, right, in terms of function value, right? So we take a small step to over here, and all of a sudden the function value jumps up, right, to something crazy. This is one of the problems with the gradient methods in general, right? That it's not clear how to choose the step size in practice, right? So we saw some ways to get around this particular issue, right? Where we essentially did an exact line search or an approximate line search to find a good step size, right? And the reason we needed to do something like this is exactly this, right? Because the approximation we were making, right, it essentially was just linearizing the function around our current best guess for the solution. So if these are first order methods, then second order methods are those kinds of optimization procedures to take advantage of not only the first order approximation, right, basically the best approximating hyperplane, but they also take in higher information about higher derivatives into account. So the difficulty with higher derivatives is that they can often be expensive to compute. So we'll see some examples later on today, and I'll explain exactly why they're much more complicated to compute than they are than the gradient is typically. This is more of a problem for multivariate functions than it is for univariate functions. But the benefit that you get of looking at this second order information is you can often get algorithms that converge much more quickly. So in general, second order methods are those methods that use the first three terms of the multivariate Taylor series expansion. So far we've been using this first order piece, right? Just this little chunk here, right, where we approximate f of x by picking some point, say x naught, and computing the gradient at x naught, and then what's inside the red box there, right? That basically is the function that describes the supporting hyperplane to the function f at the point. Now we're going to add the second order piece to the Taylor series. So that's this term right here that involves the second derivatives. So remember, for a multivariate function, that the Hessian matrix h sub f evaluated at a point x hat is the matrix of second partial derivatives. So the ith entry of this matrix is the second partial derivative of f with respect to xi and with respect to xj. And remember, ordering doesn't matter, so that it doesn't matter which order you take the partial derivatives in. If you take the partial derivative with respect to xi or xj first, is the same as taking with respect to xj and xi first, assuming that f is twice continuously differentiable. So if the derivatives exist everywhere, then we can form the second order Taylor series expansion. Right. Now, it's important to note here again that, right, we really do need the derivatives to exist. and the second derivatives to exist, right, in order to apply methods, there's sort of not as nice of there's not a sort of as nice of an approach as the subgradient method was for second order methods. We'll have some discussion of that a little bit later on. But we really need the derivatives here to exist. Otherwise, we can't compute, well, at least for the method that we'll see today, we won't actually be able to do any of the updates, right? We actually need to be able to compute this Hessian matrix essentially in closed form, right? Be able to need to compute all of its entries. Okay. Just a little bit of a notational thing to point out is I've been in this course referring to this Hessian matrix by writing H sub f. The book and sometimes some other things that you might read will write this as like grad squared f. I prefer this notation because sometimes the grad squared one is a little overloaded in my opinion. So there's some other places where it's used too and not quite to mean the Hessian matrix. So I prefer this H just to make it clear, right? But it is an n by n matrix, right? So if we're talking about a function of n variables, then there's n squared elements in this matrix. So what is the interpretation of the second order Taylor expansion, right? So well, the first order Taylor expansion, right, it's the best linear functional fit for the function at the point x naught locally. So the second order Taylor expansion then is the best quadratic fit locally at a particular point. Right? Now it won't be the exact function, right, unless f is quadratic, right? It won't be the exact function, right? It'll be some approximation of it, right? This is why I write this little squiggly approximation line. There's some higher order error terms here that depend on, that are basically cubic in x. But it's a good local approximation of the function, right, with a parabola or a paraboloid and in higher dimensional spaces. Okay. Just a reminder, so we're going to make a little bit more use of the Hessian matrix today. We haven't really used it at all in the past, right? So the last time we've actually really seen it and in any detail was in lecture 1, like the very first lecture in the course, where we saw that for convex functions, the Hessian matrix is always positive semi-definite. So I wanted to remind you of some facts about the Hessian matrix. We'll see some more as we go along. The first is I just want to remind you what this quadratic form looks like. So if you have a matrix A and a vector x, so here we're assuming that x is some n-dimensional vector, and A is some n by n dimensional matrix, then the operation x transpose AX, if you write that out mathematically, what that is it sums over all the entries of the matrix A, so over all I equals 1 to n, of Aij times Xi Xj. Right, so the diagonal term, so for example, the 1, 1 entry would be A11 times x1 squared, right? And the off-diagonal terms look like, A12 times x1, x2. Okay. So this is a quadratic form, right? It's a polynomial of degree 2 in all of it's a sum of monomials, right? All of which are, of degree 2. In each of the variables. So this is a quadratic form, right? We saw similar things, right, when we were looking at quadratic programming problems. Okay. Questions about this second order Taylor expansion or this Hessian matrix? I'm going to start off by doing the univariate case in a minute, so we won't have to worry about computing this matrix for a little while. But I still want to make sure that everyone is happy with how one would compute this thing, and sort of what the notation is meaning. No questions? Someone maybe just post in the chat to let me know that you're alive. Was there a question? Someone wrote after the example. I don't know if that was a specific question or just another way to say I'm alive. Okay. Great. All right. So let's move forward. So there are kind of a wide variety of second order methods that are pretty popular. So today we're just going to see one of them, and the first one is called Newton's method. There are kind of two variants of Newton's method that get some popularity in practice: Gauss-Newton, quasi-Newton. And then there's two second order methods that are really sort of the most practical, called BFGS and LBFGS. The BF and GS are names for it's named for the people that designed the method. These particular methods, which I think I don't know if we'll go into great detail with them, but I'll probably show them to you at a later level. These methods are actually probably the most practical. So, for example, in machine learning and artificial intelligence, when people are using second order methods, these are probably the methods that they're using. They turn out to be sort of the most efficiently implementable in practice, and they have some other nice features. One of their nicest features is they don't actually require you to compute the Hessian matrix yourself, which we'll see is sort of the bottleneck of these second order procedures in a little bit. So today, though, we're just going to talk about the simplest of the methods in order to just sort of get started, and that's Newton's method. So to make the discussion simple, we're also going to talk about unconstrained optimization again. So no constraints here. We're going to just be talking about minimizing twice continuously differentiable functions over all of Rn, right? So we won't make any constraints. We'll see shortly that the approach to this first simple Newton's method can actually be very easily adapted to the constrained setting without too much effort, and that's also true somewhat for the remaining methods. But let's start with the easy case to build some motivation, and it's also a little bit easier to visualize. Okay. So like I said, we're going to start with a univariate case, so let's just assume someone gives us a function of one real variable with one real output. So Newton's method, so you may have seen it. So sometimes in a calculus class, maybe either in high school or at the college level, you might see Newton's method. Typically when you see it as a root finding algorithm. So Newton's method was originally designed essentially to solve equations of the form f of x equals 0 for x. So the idea about how it works is similar to the same kinds of ideas we were using for our first order methods. So you take the function f, you approximate it around a particular point, let's say xt, right? Again, you should think of xt as the teeth iteration of our algorithm. So its first order Taylor expansion, right, is basically just the linear hyperplane or the tangent line. In this case, because we're in one dimension, it's the tangent line of the function f at the point xt. Because we're trying to find a place where f of x is equal to 0, right? We approximate f with its first order expansion, and then we just solve the first order formula explicitly, right, for x. So that should be a t. Sorry about that. So we solve f of xt plus f prime of xt times x minus xt equals 0 for x. When we do, that gives us that x should be equal to xt minus f of xt all divided by f prime of xt. And so we'll just set our next iteration, xt plus 1, to just be equal to xt minus that thing, the solution to the first order equation. So basically, when you take a function, you approximate it by a line, right? What we're looking at here is where this line intersects the x-axis, right? That's what we're going to use as our next iteration. So in pictures, it looks something like this. Here we've got some function, and let's suppose this is our current iteration. We're at this point right here. So to apply Newton's method to find a place where this function is equal to 0, we would first compute the gradient. When we do that on this function, to the best of my artistic ability, this is a line that is tangent to this function at that point. Right? We're using this now as an approximation for the function f of x. So we find where the tangent line crosses the x-axis. That's this point right here. We then step to that point. Right? So at the next iteration, we've moved ourselves to this new point, to this new red point, right, given by the intercept of the gradient of the best first order linear approximation to our function at the previous point. And then we just keep repeating this procedure, right? We compute the gradient here. That gives us an intersection with the axis right around this point right there. We then step to that point, right? So we're not quite at the place where f of x equals 0, but if we keep repeating this procedure, we will indeed converge to this point right there, right? The optimal point is like right here somewhere, right in that little region. Now, you'll note that there are multiple places here where f of x is equal to 0. The algorithm is only guaranteed to find one of them, right? So sort of by analogy to gradient descent, right? Gradient descent for a non-convex function, right? There could be many places where the derivative is 0, right? So depending on where you start, you will probably converge to different solutions, right? As an example, right, if we had started this procedure right over here at this point, constructed the tangent line, let's see if I can do this. Tangent line, something like this. I thankfully have a ruler on my desk, so tangent line, something like this. We would look at its intercept, and we would probably converge to this crossing point over here, right? If we iterate Newton's method starting from that point. Okay. So it's a pretty simple strategy, right? Compute first order approximation, look where it crosses the x-axis, and just move to that point, right? Just solve that simple linear function, figure out where it crosses the x-axis, and step directly to that point, right? And just keep repeating this procedure until you get to a point where f of x is less than or equal to epsilon, right? So you get arbitrarily close, right, to a good solution. Okay. Good. Questions about the method? So hopefully it's pretty easy to understand, right? It's not nearly as complicated as really even the two different optimization methods that we just kind of quickly reviewed. So there's a question: is this representative of the second derivative? No. So far there's no second derivatives, right? This is just a first order approximation. I've preempted your question on the next slide, so hold that thought. Questions about the basic method, though? Okay. Right, so as we just asked, right, I thought we were talking about second order methods. We are. So Newton's method, typically, sometimes people would say like Newton's method for optimization. would apply this root finding strategy to find the zeros of the first derivative, right? If we're looking for a place where this function has a local minimum, right? It would make sense that we should seek a place where the derivative is equal to 0, right? So instead of applying this root finding algorithm to the actual problem, right, to the actual function f, we would apply the root finding algorithm to the first derivative. So what does that look like? Well, we would basically compute the first order Taylor series expansion of the first derivative, right, which looks like this. So you take f prime of x and you approximate it as f prime of xt, right, for some fixed iteration, plus the second derivative, right, times x minus xt. Right, this is the first order Taylor series expansion of the derivative. We would then compute the update, right? Set this equal to 0, right, and solve for x. Gives us the update that our next iteration should be chosen by taking our current iteration and subtracting from it the first derivative divided by the second derivative at this point. So it turns out that this is actually equivalent to minimizing the second order approximation. So let's just write that down really quickly to see it, right? So right, the second order approximation of f around the point xt would look something like f of xt plus f prime of xt plus 1/2 times f double prime of xt, right? The second derivative at that point. So this is the second order Taylor series expansion. If we wanted to minimize this function, right? So this is a quadratic function. Oops. So I forgot the most important part with the x's. Those are just the constants. Right? F prime of xt times x minus xt plus f double prime of xt times x minus xt squared. Now it looks like a quadratic function of x's. So if we want to minimize this function with respect to x, right? So now we're taking this quadratic function, we're using it as a surrogate for f, right? So just write little squiggly lines there as a surrogate for f. Then we can take the derivative of this thing, set it equal to 0, and solve. So when we take the derivative of this thing, we get, well, this term disappears when we take the derivative, as does this piece, because xt is a constant. We're taking a derivative with respect to x. So we get the derivative is f prime of xt plus, well, the derivative of this piece, again, it's important that there's a 1/2 out front, is 2 times x minus xt, right, times f double prime of xt. So we just get f double prime of xt times x minus xt. At the derivative, we set it equal to 0, and we solve for x. Right, so that's exactly the same thing that we did, right, by taking here, right, by taking the Taylor series expansion of the first derivative, right, and then using the root finding algorithm. So I don't have an amazing picture of this, but if we kind of go back to this for a second, I can probably illustrate. Let me just erase everything. Oops. Second. So as an example of what this procedure is doing and how it's a little bit different. So here, right, what we saw, right, this was done by computing the first order Taylor series expansion, right? If we were going to apply Newton's method for optimization here, let's say starting at this point here, we would first compute the best quadratic approximation for this function locally, which might look something like, I don't know, it's kind of hard to draw this, might look something like this. That's not it's probably not going to look like that at all. It's going to look something like this. The minimum is going to be like somewhere down here. And it looks something like this. We compute the best quadratic approximation for the function at this point, and then we find where its derivative is equal to 0, right, which is just this little minimum right here, and then we would step to that point. Right. It's sort of harder to draw the quadratic piece because although the first derivative has this nice expression in terms of the tangent line, the second derivative, right, it's a tangent line to the first derivative, right? So it's harder for me to draw, in some very coherent way on the plot. But this is essentially what's happening. You compute a second order approximation, you minimize that second order approximation, and you step to that. Okay. So in this course, this is what we'll refer to as Newton's method. We'll basically always be applying Newton's method for optimization. So we'll always be applying it to the first derivative, and that requires us to compute the second derivative. So that's why Newton's method is considered a second order method, because in the end, right, it's basically computing a little parabola or paraboloid when we get to the higher dimensional case around our function at a particular point, minimizing that parabola, paraboloid, again using the fact that it's easy to solve that optimization problem, right? And then we just step to the solution of that optimization problem. So in particular, right, so Newton's method will always be like perfectly exact whenever the actual function you're trying to minimize is a quadratic function. So what I mean by that is that if f itself was a quadratic function, then Newton's method would step directly to the optimal solution. Why? Because at that point, the second order Taylor series expansion is exactly the function. Right? For a quadratic function, it's equal to its second order Taylor series expansion. So when you solve for where the derivative is equal to 0, you'll step directly to the optimal solution. So this is in contrast to gradient descent, right? Which of course would still require iteration even for a quadratic function, right? Because it's not using any information about the curvature of the function. Okay, questions about applying Newton's method to the first derivative? I'm judging by your lack of questions that hopefully this is pretty easy, at least in comparison to the things we've been doing recently, right? It's kind of intuitive. It's not so heavy on the algebra, and it's sort of easy to kind of keep track of in your head. Okay. So the multivariate version of Newton's method is exactly the same thing. There is a question. So wait. Oh no, that's an older question. Never mind. Okay. So the multivariate version of Newton's method, is based on the second order Taylor series expansion, for multivariate functions. So by complete analogy to the univariate case, right? We just take that second order Taylor series expansion, we take its gradient, we set it equal to 0 and solve, and that gives us the update. The difference is now that when we take the derivative in the gradient in the multivariate case, right, we end up with a matrix problem, right? So let's go back to the slide for a second. Right, Taylor series expansion. When we compute the gradient of this thing, right, we get with respect to x, we get the gradient of f at x naught plus the Hessian matrix evaluated at x naught times x. Right, the derivative of this second term, right, is just h of f at x naught times x. We set this equal to 0 and solve, right? So rearranging, right, that tells me that x should be equal to the inverse of this matrix, right, times the gradient. I should switch my pen color back to red instead of that awful orange. So we can see automatically that this is a little bit more complicated, right? Because unlike the univariate case where computing an inverse is easy, in the multivariate case, we actually have to invert a matrix, right? So if you remember from linear algebra, right, the inverse of a matrix is the matrix such that when you multiply it by its inverse, you get the identity matrix. The difficulty with inverses is they don't always exist, right? So as an example, right, in the univariate case, right, if we wanted to compute this update and the second derivative was equal to 0, right, we wouldn't know how to proceed, right? We'd get stuck. And the thing is that in such a situation, right, we can see, right, by the formula below here, right, if the second derivative is equal to 0 in this equation, right, or this equation, right, then there might not be any solution for x, right, that actually gives you 0 here, right? Because unless f prime of xt was equal to 0, right, this whole expression would not have a solution, right? There'd be no solution to this equation. The same thing happens in higher dimensional space, right? It's possible, right, that the matrix, is not, the Hessian matrix is not invertible at a particular point, right? Essentially the multivariate equivalent of 1 over 0. And when this happens, there could either be infinitely many solutions or no solutions to the equation, right? Gradient plus Hessian times x equals 0. So because of this, right, we have to be really careful when we apply Newton's method. If we ever end up in such a situation, we're in trouble and the method can't proceed. So what are the places? So I guess quick question for everyone here, right? Just remember our basic high school calculus. What are the places where the second derivative is equal to 0? Right? Let's just think univariate case for a second. What are those points called? Does anyone remember? Yeah, they're inflection points, right? They're the points where the function basically goes from being convex to concave or concave to convex, right, locally. Now, although this is kind of annoying, right? So like, it's possible that like lots of functions have, right, inflection points, right? This is not true, right? In the univariate setting, right? If we had a convex function, right, there are basically no inflection points, right? Because the function never goes from being, convex to concave when it's convex everywhere. Now, the difficulty is that you can still have the second derivative equal to 0, right, if you're in a place where the gradient isn't changing, right? So although like more generally there are inflection points, you can still have places, even for convex functions, where the derivative is equal to 0, because the convex function could just be flat there. Right? This is why we typically refer to the second order methods as approximating the curvature of the function, because as long as the function isn't a straight line, the second derivative tells you something about the rate of change of the derivative, right? So as long as it's not a horizontal line somewhere, we're okay. So we can basically make sure that this always happens in practice, more or less. So it's not such a big deal, typically. The thing that prevents you from using Newton's method is often not the lack of inverse of the matrix. It's some numerical issues related to computing inverses, which I'll come back to. I'll come back to in a minute. But it is important to point out that if you would be very unlucky and step into one of these points, then the algorithm can't proceed. You would just have to terminate right there. That you can't make any more progress. At that point, you might just restart the optimization procedure and hope that you're more lucky the next time around. Now, in practice, right, even though, let's even assume that the inverse exists, computing these inverses is often quite expensive. So the computational complexity of computing the inverse is big O of n cubed for an n by n matrix. So this is even true if the matrix is symmetric. It's an expensive operation. So typically in a lot of applications, for example, machine learning, artificial intelligence, we don't consider algorithms that operate on the scale of n cubed as efficient. So even though, like in your algorithms class, anything that was polynomial time you declared to be efficient, that's in practice things that scale like n cubed are often prohibitive, right? You can't really apply them. If we're applying this to like a 1,000-dimensional problem, then this thing scales like 1,000 cubed. It's not great, right? That's really expensive, right? And this is just for one iteration of the method, right? You have to do this at every iteration. This is why, you know, if you've taken a machine learning class or you've done a lot of sort of practical work in other areas where these kinds of optimization methods are applied, you've probably not used a second order method. And it's really why, you know, in most of sort of modern machine learning, the literature is sort of dominated by gradient methods. On top of the expense that's required to compute the inverse of the Hessian matrix, computing the Hessian matrix itself is often expensive, right? There's essentially order n squared partial derivatives, you know, pairs of partial derivatives that need to be computed, right? That in itself can be expensive. So the whole procedure has a really, really big expense built into it, right? You know, in the univariate case, it's not so bad because the Hessian matrix is just a single number, right? But in the multivariate setting, it kind of scales poorly with the dimension of the optimization problem you're trying to solve. Still, there are times when it is very beneficial in practice to do this, and these second order methods are the motivation for some first order methods, namely the accelerated gradient methods, which are incredibly popular in practice, and we'll come back and talk about, I think, after we wrap up a discussion of second order methods. Those, in fact, are very practical, and they basically seek to emulate this behavior of the second order methods, where they basically use the second order information to make choose better descent directions and better step sizes, etc. So in practice, it can convert, these kinds of methods converge much faster than gradient methods, but they're often much less robust. They can be really sensitive, right? If you've got a function that's close to being, that's invertible, but barely invertible, right? There can be some numerical issues with solving the system, you know, computing, you know, hf of xt inverse times the gradient, right? Actually solving that system to get a solution, etc. So again, you know, we'll get to practice a little bit with them on the homework, so you can see. But they definitely have a much higher overhead than the gradient methods. Okay, let's see some pictures. So I put together some simple illustrations. So here is just this is a bivariate function. So again, what's being shown here are the contour lines of this two-dimensional function. Its minimum is in this dark purple region, and the function is almost quadratic, not quite. It's got this x to the fourth term, which is making it non-quadratic. The first thing I'm showing here is the gradient descent method with a diminishing step size rule. So this would have been our classic approach to solving a problem like this, right? That we would have done for a general unconstrained optimization problem. You can see that the algorithm takes a big step at the beginning and then makes relatively slow progress. The reason that the gradient method struggles a little bit in this particular application is that the slope of this function is in fact quite steep. That the x to the fourth term at the beginning here makes it so that the derivative can be quite large as you get far away from zero, right? That's why this first step was so big, right? It starts off at -5. The derivative there, right, is -5 to the third times 0.1, right? So the scale of things is larger because the derivative is much larger for this function. So let's contrast this with Newton's method applied to this strategy. applied for the same optimization problem. And you can see basically within 5 or 6 iterations, Newton's method has converged to the optimal solution. And in fact, at this point, when I produced this plot, after 6 iterations, the gradient has norm less than 10 to the negative 16th. So this is converged as converged can be. It is basically just steps to the optimal solution in about 5 or 6 steps. And you'll note here, we didn't use any step size or anything, right? This thing is stepping based purely on the local curvature information, right? Approximating this function locally, right, with a little quadratic, right? Minimizing that quadratic and using that to determine where it should step next. Okay, questions about this? So for this particular example, it was it's a 2-dimensional problem, so it's relatively easy to compute the inverse. So maybe let me just show you what the Hessian matrix is here, right? So the Hessian matrix of f of x, y, just sort of to drive home this point. Well, what does it look like? It's 2 derivatives in x, so that's going to look something like the first derivative of this is 4x cubed. The second derivative will be 12 x squared. So the first entry of the Hessian matrix will be like 0.1 times 12 times x squared. The other terms, plus 2. The first 2 terms are the only 2 that have a non-zero second derivative with respect to x. When we go to compute the off-diagonal elements, so that's computing the partial derivative of f with respect to x and y in any order that we want. So for this, we only need to look at the term that involves terms of this expansion that involve both x and y. So that's just this middle term right here, this negative x, y term. The second derivative of that is just -1. And then we need to take 2 derivatives with respect to y. And for that, we get, 2 times 0.5 and just 1. Right? So that's what the Hessian matrix looks like for this particular problem. So basically, it only depends on x for the first entry in the matrix, because the other entries, the second derivative is a constant essentially. So then I just invert this matrix and multiply it by the gradient in my current iteration, and that gives me subtract that from where I currently am, and that gives me the new place to step. Okay. Questions about these examples or Newton's method so far? Perhaps the biggest question, right, we could ask is, how do we know that this procedure actually converges to something, right? Maybe we just sort of bounce back and forth forever and never make progress, right? Our intuition for the gradient methods was, right, when we compute the gradient, right, calculus guarantees us that taking a small enough step in the direction of the negative gradient will always result in a functional decrease, right? That's the promise that we get from calculus for first, one continuously differentiable functions. We no longer have that. It seems like we no longer have that here, so it's not clear why this procedure should converge. We'll come back to that in a second. I want to make sure there's no questions though about the procedure generically. Give you 20 seconds to think about it, and then we'll just move on. Okay. So it turns out that this update computed by Newton's method, right, actually does correspond to a descent direction under certain conditions. So this looks a lot like our gradient update, right? In gradient descent, we would have updated, xt plus 1 is equal to xt minus some step times the gradient of f at xt. So the only difference, right, is that we're multiplying by the inverse of the Hessian matrix here, right, instead of choosing a fixed step size and multiplying it by the gradient. It turns out that the negative, of the inverse of the Hessian matrix times the gradient actually is a descent direction when f is a convex function. So remember, right? So remember what that means, right? If it corresponds to a descent direction, it means that we're guaranteed that if we take a small enough step in that direction, the function will decrease. To see that it's a descent direction, right? We need to remember two things about Hessian matrices, and one about directional, one around directional derivatives, and one about Hessian matrix. The first is that when a function f, multivariate function f is convex, that means that its Hessian matrix is positive semi-definite everywhere. So a matrix A is positive semi-definite if x transpose AX is greater than or equal to 0 for all x. So again, right, this x transpose AX is just a quadratic function of x, right, that we get by summing over all I and j of aij times xi xj. If that's greater than or equal to 0 for all x, then we say the matrix A is positive semi-definite. In fact, in order for the inverse to exist, we need something stronger. We need the matrix A, or the Hessian matrix, is positive definite. Positive definite, you replace the semi with a definite, and this greater than or equal to 0 with a greater than 0 for all x not equal to 0. So we need more than just positive semi-definite. We actually need positive definite so that the inverse actually exists. If that's the case, then in order to determine whether or not this is a descent direction, right, we ask, right, is the function decreasing along the direction, minus hf of xt inverse times the gradient? Remember, to check whether or not the function is decreasing in that direction, we can compute the directional derivative, which we do by taking this direction and dotting it with the gradient. So if I dot this thing with the gradient, right, so I take gradient of xt, gradient of f at xt, and I dot it with this direction, I get this following function, right? And because the Hessian matrix is positive definite, its inverse matrix is also positive definite. We'll prove that result a little bit later on when we talk about numerical linear algebra methods. Then this expression here looks like x transpose h inverse times x with a negative sign, so it always has to be less than or equal to 0, and in fact it's always less than 0 as long as the gradient is non-zero, which tells us that this direction minus h inverse times the gradient is always a descent direction whenever the function is locally convex. So what that tells us is that basically Newton's method should converge, right? Because it defines a descent direction, and in fact, for appropriate step size, we know that that it's always possible to make progress by stepping in this direction. Now, the way that we defined the method, there was no step size involved, but we could add one. And in fact, in practice, people often do add a step size to Newton's method. One other thing to point out about this dot product, right, is that tells us this is literally the directional derivative in the direction, right, specified by Newton's method, right? Sometimes it's called the Newton step, or the Newton direction. This thing, right, is, as it gets closer and closer to 0, right, that's a good approximation for convergence, right? That's telling us that the largest step that we can take locally is going to 0, basically, right? The derivative in that direction is going to 0. The gradient in that direction is going to 0. This is the stopping criterion that the book proposes. So if you follow along and read the book's discussion of Newton's method, you'll see that they use the stopping criteria. But it's a gradient method. We can use any stopping criteria we want, right? If you want to stop when the gradient is close to 0, like we would have done, right, for a regular unconstrained gradient method, right? We can still do that here. It still makes sense, right? Because we're essentially doing gradient descent, but with a different kind of with a different direction to step in. So the book actually gives some other intuition about this as well. They show that this is actually the steepest descent direction under a different notion of distance. So instead of the Euclidean distance, you can use the Hessian matrix to define another distance metric, and this is sort of the steepest descent direction under that norm. So if you want to know more about that, you can read it in the book. It's kind of a neat observation. But regardless, it's a descent direction, and so all of those stuff that we have for gradient methods applies. So it's somewhat nice, right? So this is a second order method, right? But we can apply basically all of our knowledge about first order methods, right, when we use it. So in particular, we can do anything we would have done with gradient descent, right? We can choose different step sizes. We can use line search, right? So exact line search or backtracking line search, right, are also both very popular. So using line search methods in Newton's method is pretty popular in practice and in different implementations. Again, I'm pretty sure the book's implementation probably does some kind of line searching, right? At least their sort of fanciest implementation will do some kind of line search. I do want to make one computational note about this method. So the way we've written the update here is that, right, you would compute the inverse of the Hessian matrix and multiply it by the gradient. So you can do that. And, for example, on the homework, if you want to implement Newton's method, right, there is a method in NumPy, right, in Python that will compute the inverse of the matrix for you. But it turns out that that's actually typically pretty inefficient. So most numerical methods packages have a special routine that just solves linear systems. So technically, we're solving the linear system, right? Gradient, right, or the Hessian of f, no squared, of x at some point times. So let me remember to go back to the formula, right? Just times x, I guess, right? Has to be equal to the gradient, right? We're solving this linear system. So there's special methods that will just solve these linear systems, and they're often much faster and much more numerically stable than computing the inverse. The reason for that, like I said, is that there's, and I think I'm going to put a little bit of this on the homework. It'll be our first sort of kind of foray into numerical issues that can arise in practice. When basically the eigenvalues of the Hessian matrix get close to 0, so that the matrix gets close to being not invertible, there can be there's a significant issue with computing the inverse, like explicitly computing the inverse. However, solving the methods that solve the linear systems are numerically stable against those kinds of issues. So we would say that in this situation, the problem is ill-conditioned, right? If the Hessian matrix has eigenvalues close to 0, and as a result, it's not a good idea to compute the inverse. However, you can find these more stable numerical methods basically in any language you want. So, for example, in Python, NumPy has a method linalg.solve, which basically solves linear systems of this form. And you don't actually have to compute the Hessian matrix, right? It finds the x that solves this equation, which is equivalent to computing the inverse of the Hessian matrix times the gradient. That's just a numerical note. Like I said, I'll put some more detail on some of the numerical issues related to this stuff on the homework, so we can get a little better understanding of why there can be potentially some numerical issues here. Right? This is why the second order methods are a little bit less robust than the first order methods. They're a little bit more sensitive to these kinds of numerical numerical issues that you have when computing these things. Gradient descent by itself is actually pretty robust. In fact, in practice, you can even get away with approximately computing the gradients, right? Like we saw in homework 1, right? And it doesn't really kind of run into these numerical issues that we will encounter with Hessians. Okay, questions about any of this? I think that's all I wanted to cover for today. In Wednesday's class, we'll talk more about some other second order methods. Some of them we'll talk at a little, like I said, we'll talk at a little bit higher level, like BFGS and LBFGS. I'm basically just going to introduce you to those things, just because I think it's really important that you know what they are, so that if you ever get to a place in your life where you need to use a second order method, you know what exists and you can apply it. But we won't go sort of into like the nitty gritty details of those methods, because to understand why they really work is really quite a challenge, because they're much more sophisticated in some ways than what we've got here. Okay. Good. Any final questions about Newton's method? Well, you guys were very quiet today, but I guess we'll stop here.